In the previous video, we talked about how we can set up a direct sequence. So let me go in slight more detail for a direct sequence. Let's say you have 20 moles of A, 20 moles of B, 20 moles of C, and 20 moles of D in your feed stream. And let's say you have perfect distillation columns, some magical ideal distillation columns that give you 100% perfect split. So in your first column, the split between A and B, all of A goes to the top, everything else at the bottom. So now you have 20 moles of B, 20 moles of C, and 20 moles of D. So for the direct sequence, all the products are withdrawn in the distillate. Alright, and etc. etc. Oops. Yeah, 3 distillation columns, 4 species does it. So what I want to say is, what I want to point out is how much fluid each column is processing. The first column is processing the entire feed. So that's like a total of 20 plus 20 plus 20 plus 20, 80 moles of fluid, 80 moles of feed. So the more feed a distillation column has to process, the wider the diameter of the column needs to be. There's going to be like higher operating costs, higher reboiler duty, higher condenser duty. So those are the things that need to be kept in mind when coming up with a design. So the first column processes 80 moles of fluid. The second column processes 60 moles of fluid, and the final column processes 40 moles of fluid. So one of the drawbacks of a direct sequence is that each column is going to have a really high load, a really high fluid load that it needs to process. On top of that, let's say if something goes wrong at the bottom of the first distillation column, will the second distillation column be operational? Well, not anymore. Similarly, the third distillation column will no longer be operational. So this is the problem with having all your distillation columns in a series sequence. One thing messes up, everything down the drain is gonna be shut down. So let's see if we can remedy that situation. Let's come up with an indirect sequence. We still have 20A, 20 moles of B, 20 moles of C, and 20 moles of D. Now in the first column, let me define a split between B and C, B being my light key and C being my heavy key. Alright, so now once again I'm assuming magical ideal separators. So 20A and 20B goes to the top, 20B and 20C goes to the bottom. Alright, so now in order to separate A and B, A goes to top, B goes to bottom. So now notice how this column is processing 40 moles of fluid. Well, the original column is still going to process the same moles of fluid, and this bottom column for B and C, C and D, $20 moles C come on top, 20 moles D come at bottom. Okay, now let's compare the fluid loads. First column 80, second column 40, third column 40. So that's a total load. So the total load of this column is going to be 80 plus 40 plus 40, 160 mole. Now that's obviously not the actual number of moles it's processing, but it's a rough estimate. Compared to this distillation train, we have 80 plus 60 plus 40. We have a total of 180 moles. So this sequence is processing it's processing 20 fewer moles. And second, if something goes down in one of the lines, let's say if something bad happens at the distillation at the distillate of the first column, the A and B column will need to be taken offline, but the C and D column is still going to be operational. So there's a bit of redundancy, which is really desirable in your chemical plants. Also, the lower fluid load means that your columns will not gonna be as thick, and the reboiler and condenser duties are gonna be lower. So it's gonna save you operating costs as well as capital costs. More about that in future videos. So these are just like some of the few possible sequences that you can come up for a separation for like multiple chemical species. There are more, so but like, and obviously you need to like run simulations using aspirin to find out which one is the best. And then there are like even more variables that you need to optimize, like the reflux ratios, the vapor boil up feed, to like further optimize the design. But in order to optimize the design, there needs to be a base design in the first place. So if in order to come up with a base design, engineers usually use some rule of thumbs. Now rule of thumb basically means, seniors are going to hear this word a lot thrown around in their final year. So rule of thumbs basically means guidance from experience. Some people thought like a certain things worked in the past and they've shown to work, so they just like stuck with some conventions. Here I have 5 rule of thumbs for designing distillation column sequences. Obviously there are more in your textbook for process and product, but you want to come up with a distillation sequence that checks as many boxes as possible. The first rule of thumb being that you want to remove the largest product first. So the product in your feed that has the highest concentration, it's going to be easier to separate it first. So you might want to get that done ahead of all the other separations. The second one is also tied to the first one, easy separation. You want to perform the easy separation first. And now the easiest separation is not always the product that's in the largest concentration. Easier separation between two species that have the highest differences in their volatilities. And also 3 and 4 are more about the safety and operability. So if one of your products is sensitive to heat, like for example if you have a acrylic acid that polymerizes at like higher temperatures, you want to remove it in the distillate because distillate runs at a lower temperature than the bottoms. Remove the hazardous materials first. So this is part of like a safer design. Remember that safety is like the number one priority in any design. Lastly, you don't want to over purify any of the products. So because like over purification means more cost. The more as long as your products hit the specs as long as you hit specs, whatever, and those specs might be whatever are specified by the client. You don't need to perform any more work, because the rate on return on that extra work is going to be, well, zero, because the consumer doesn't care if he gets a 99.9% product when he only asked for 98% product. So keep those things in mind. In next sequences, we're going to go about the sizing of distillation columns.